Hi everyone, welcome to Lecture 8, which is about the planet Mars. In the previous lecture, Lecture 7, I talked about the 8 planets, but in reality, I excised 2 of them from the lecture. I didn't talk about Earth because we had mentioned that in a previous lecture, and I didn't talk about Mars because, as I mentioned in that lecture, Mars was to have its own video, which is this one. In this video, I'm going to talk about some of the basic characteristics of Mars, as well as the past and present missions that we've sent to Mars and are sending. And actually, there are future missions that are on their way to Mars. There are rovers and orbiters, but I'll talk about those in a separate video. Mars is a very important planet. I just want to say this before I continue, because, well, we'll talk about some of the reasons, but basically because it's a terrestrial planet. There's evidence that in its past, it was much more like Earth than it is today. Today, it's very dry and cold and barren, but in the past, we know it had liquid water, as we'll talk about. And as a result of these facts and others, we've sent a disproportionately large number of missions to Mars. And that's why we're giving Mars its own lecture. Let's talk about some of the basic properties of Mars and characteristics. The first is that Mars is the 4th planet from the Sun. The order goes Mercury, Venus, Earth, Mars, and then Jupiter. So Mars is the last terrestrial planet going from the Sun outward. Notice here we have a couple differences between Mars and Earth and then some similarities. Or you will notice, I should say. One of the differences is that Mars is substantially smaller than that of Earth. Its mass is only about 10%, a little bit more than 10% of Earth's mass. Its radius is about 53% of Earth's radius. And from these 2 facts, we can actually calculate the surface gravity, which is about 38% that of Earth's. That means that if you weigh 160 pounds on Earth, for example, you'd weigh about 61 pounds on Mars. You can compute your Martian weight by taking your weight on Earth and just multiplying by 0.38. I do want to mention something that might be confusing you here, and that is that when people talk about losing weight or gaining weight, they really mean mass. You might be confused as to how your weight can suddenly change if you go to Mars or the Moon or space. Because if you get in a rocket ship and you go to Mars, you don't suddenly lose most of your mass. And indeed, that's true. Your weight is actually the force that gravity is applying to you. It's the force of gravity on you due to some planet or moon or whatever is near you. And therefore, if you go out into the vacuum of space, your weight will go to 0. If you go to the International Space Station, for example, your weight suddenly goes to 0. Your mass doesn't change. Your mass is an intrinsic property of the number of molecules you have in your body and the type of molecules. And you can only change that by changing diet, etc. You all know about that. But the weight that your body has can be changed easily if you just go into space. Let's talk about a similarity between Mars and Earth. This similarity actually could be quite important if we want to send people to Mars, and that is that the Martian day is almost exactly the same length as the Earth day. It's about 3% longer. We all have natural biological rhythms that depend on the length of the Earth day. There's no law of astronomy which says that a day has to be 24 hours or consists of a certain number of seconds or what have you. That just happens to be the length of the Earth day. Mars has a day which is very similar in length. A Martian year actually differs from an Earth year. It's almost twice as long. It consists of about 687 Earth days. Mars has days and nights, by the way, for the same reason that Earth does, because it rotates on its axis. Mars has 2 satellites. This is a difference between Earth and Mars. We have one, the Moon. The satellites around Mars, these are natural satellites, moons, are Phobos and Deimos, and these are much smaller than Earth's moon. Let's talk about a major difference between Earth and Mars. The Martian atmosphere is much thinner than Earth's atmosphere. It's about 0.6% that of Earth's, measured in pressure. And even if the Martian atmosphere were breathable, which it isn't, we'll talk about that in a second, the atmospheric pressure on the surface of Mars is way too low to sustain human life. Basically, we have water in our bodies, not basically, we do, and essentially this water, we could argue, would begin to boil at the human body temperature of 37 degrees Celsius if the pressure drops below a certain limit, and that limit is well above the atmospheric pressure of Mars. This is somewhat of a simplification, but it's roughly correct. This is the explanation you'll find if you look this up as to why we cannot live in very low pressure environments. It's basically because the water in our bodies would begin to boil because the boiling point of water increases as the pressure increases. As the pressure decreases, the boiling point decreases, and eventually the boiling point can go below the human body temperature of 37 degrees Celsius. This we can't change because this is natural to our biology. In any case, I don't want to get into biological explanations, but the point is that if humans go to Mars, they will need pressure suits regardless of what the components of the atmosphere are. So that's one problem. In addition, the atmosphere of Mars is not breathable. For humans, anyway. It consists of 95% carbon dioxide. Remember, our atmosphere consists mostly of nitrogen with about 21% oxygen, which is what we need to survive. Carbon dioxide is useless to us. In large quantities, it's actually deadly. The rest of the atmosphere consists of some nitrogen, some argon. Argon is a noble gas, and about 0.1% oxygen. I want to show you now a depiction of the size of Mars compared to that of Earth. This is not a two-scale depiction of the distance between Mars and Earth. Mars and Earth are separated by huge distances. Excuse me, we'll get to the distances in a bit, but this is a depiction of the relative sizes. As I mentioned, Mars is considerably smaller. Now let's talk about the distance between Mars and the Sun compared to the Earth and the Sun. The distance between the Earth and the Sun is about 93 million miles. This is a terrible way of putting it in terms of miles. It's about 150 million kilometers, but an even better way of putting it is it's 1 astronomical unit. It's a much nicer unit. The distance on average, between the Sun and Mars is about 1.5 astronomical units. So Mars is about 50% farther from the Sun than is Earth. We know that, therefore, Mars will get less light from the Sun than will Earth. It's farther away. The Sun will appear dimmer to Mars than to people on Mars, if there were people, than it does to people on Earth. So you would expect Mars to be colder, which it is. Let's talk about some of the surface properties of Mars, one of them being the temperature. And in so doing, we'll talk about some of the missions that we've sent to Mars. The first successful mission to Mars was Mariner 4, which flew by in 1965. And it took photographs. In 1976, Viking 1 was the first craft, the first craft to successfully land on Mars. This here is a photo from the Viking 1 craft in 1976. Mars has a nickname, which is the Red Planet. Actually, this is somewhat exaggerated because a true color image of Mars shows it to be a little bit grayer than this. But anyway, it has a high composition of iron, which gives it a reddish appearance. In any case, you can see that the surface is pretty barren. There's no liquid water, basically, and not much of anything except rock in the soil. Neither craft found evidence for life. This was one of the major questions. We wanted to know, is there life on Mars? But neither craft found any life, and in fact, it found Mars to be very uninhabitable. I mentioned to you that Mars has a relatively iron-rich composition, the surface, The Viking mission found that Mars was very cold. The coldest temperature recorded was around minus 120 Celsius, which is much colder than the coldest temperature on Earth. And during midday, the temperatures rose to about minus 14 Celsius, which is a very cold winter day here in New York. There is water on Mars, even though there's basically no liquid water. This photo is from the Viking 2 craft, which landed in 1978, and you can see, it's not easy to see, but if you look carefully, you can see ice on Mars. So there's plenty of water, but it's frozen. Sorry, having trouble moving to the next slide here. Okay, let's talk about Mars in temperature. This is a more updated temperature scale of Mars compared to that of Earth. This is from NASA. Temperatures on Earth roughly go between minus 88 Celsius, which is exceptionally cold for Earth, all the way up to 58 Celsius. These are the extremes. The average is around 14 Celsius. Notice that water freezes at 0 Celsius. This is an important fact. The average temperature on Mars is closer to minus 63 Celsius, and the temperature varies between about 30 Celsius, which is a very hot, not very hot, but a relatively hot summer day around this area, or maybe it's a relatively average summer day, depends on exactly how you define that, but it goes all the way down to about minus 140 Celsius, which is tremendously cold, obviously. Notice that there's a greater variation in temperature. I mentioned in the previous video that the temperature variation on Earth between different regions, but also between night and day, is reduced due to the fact that we have a relatively thick atmosphere. This atmosphere acts as sort of like a blanket, distributing thermal energy around the Earth. So it's not that every place on Earth has the same temperature, clearly that's not true, but the temperature differences would be greater if we had no atmosphere. An extreme example would be Mercury, which during the Mercury day really just burns. The temperature is way higher than anything on the surface of Earth, and at night the temperature falls precipitously down to horrendously small temperatures. Let us talk about gravity. On Mars, you would experience 62.5% less gravity than on Earth. This is actually a really nice animation that I'm going to, the link to which I'm going to post on Blackboard. So for the sake of time, I'm not going to show you the animation here, but I would like you to pause this video, go to the animation link on Blackboard about Mars and gravity, and please play it. It's a really nice animation that depicts this figure here, this person, bouncing along Earth and then bouncing along Mars, and you can get a sense of the gravity difference. Now let's talk about some of the more recent missions to Mars. In 1997, we sent the Pathfinder mission. By we, I'm talking about humans. That's my we here. This was sent by NASA, however, and the goal of this mission was to send a little craft to Mars that could explore the surface. This craft was called Sojourner, sort of a dog-sized craft. And one of the things that Sojourner discovered is that Mars once had running water on its surface. Now, in order to make a scientific discovery, you have to gather a lot of data. And so Sojourner gathered initial data which suggested that there was running water. Today, as we will talk about, we have tons of evidence that Mars had running water. So it's not preliminary anymore, and we know that there was a lot of running water. There were oceans and rivers and lakes, etc. It also confirmed that Mars has dust and dust storms. That is something else we will talk about as we get to Opportunity, the rover Opportunity. I just want to mention one quick thing. Notice that there are solar panels on top of the rover. If you think about the technical problems of sending a rover to Mars, they're actually really incredible because you need a power source for one. You don't want to just stick a battery in there. There are batteries in rovers, but the battery won't last very long. Think about the battery on your laptop or phone or remote control or whatever. It takes about 6 to 8 months to get to Mars. By the time you get there, the battery will probably be dead. And of course, you want to get there and then roam around. And so therefore, you need a power source. And the power source that we humans have been using is that of the sun, solar cells. Here are some beautiful pictures from Sojourner. The top one, okay, I'll try not to put both of these in the same frame here so you can see them more carefully. This is the sunset by Sojourner. This is not a very high quality picture, I apologize, but this is the sun. Notice that the sun looks considerably smaller as you would expect because Mars is farther from the sun than is Earth. And then this is a dust storm. Well, it's a photo of dust. It's not a storm in particular. But you can see that the sky is gray from the dust that's whipped up by the wind, by wind in the atmosphere. The next mission to Mars that I wanted to talk about was called the Mars Exploration Rover. This landed 2 craft on Mars. Spirit, and then Opportunity landed a few weeks later. Spirit functioned for 6 years, and unfortunately, the last communication was 2010, so it was defunct at that point. At that point, we had some evidence that Mars once had water, liquid water, on its surface in the past. And so these rovers were primarily tasked with determining what exactly the history of water on Mars was. Were there just little puddles? Were there giant lakes? Is there evidence that there was life on Mars in the past? And these rovers found that there's convincing evidence for flowing salty water on Mars, and that some of the rocks had formed from sediments laid down by the water. So that's evidence that water had been present on Mars for quite a long time and that it was running water. Opportunity, unfortunately, went defunct in June 2018 due to a dust storm. I want to show you a video of Opportunity. But for the sake of brevity, I don't want to show you in this video. I want you to pause this video and go watch the Opportunity video that I posted to Blackboard. And then when you're done with that, come back to this point. Let's talk about the Mars Science Laboratory. This is the most recent mission to Mars. This mission landed the rover, Curiosity, on Mars in 2012, and this rover is still active. This is a selfie of the rover, and this is not a single picture. It's actually a picture that was produced from the melding together of many pictures. You might wonder how Curiosity can take a selfie because it doesn't have a selfie stick. And the answer is that it's actually many pictures melded into one. But anyway, this is a selfie of Curiosity. This image, by the way, is closer to a real color image of Mars. I mentioned to you that Mars as a red planet has been somewhat exaggerated. It's more grayish or brownish. In any case, Curiosity's main goals are to gather evidence for the existence of life on Mars. This is, in a way, this is an overused phrase, but in a way the holy grail of astrobiology. Well, that's obvious. Astrobiology is tasked with trying to find life outside of Earth, but it's one of the holy grails of, I think, human life and curiosity. We want to know, are we alone in the universe? And Curiosity is making observations of the Martian atmosphere and the history of the climate, as well as the geology of Mars, and then to try to gather evidence from the geology of Mars for life either on Mars today, and unfortunately we haven't found any currently on Mars, or in the past. Let's go through some discoveries that Curiosity has made. It's found evidence that liquid water existed on Mars in very large quantities, lakes and rivers and oceans. This means that in the past, Mars had a relatively thick atmosphere. Recent papers that I've seen indicate that the atmosphere was probably about as thick as Earth's, maybe 50%, but on the same order. Curiosity has discovered organic molecules in ancient Martian rock. This doesn't necessarily mean that this rock contains evidence for life. You can have organic molecules without life, but what we have discovered is that all of the so-called building blocks for life exist on Mars. And in the past, there was, as I keep saying, liquid water. So that means that as far as we can tell, the surface of Mars was habitable in the past. Whether there was actually life there or not is an open question. But we have detected via Curiosity methane in the Martian atmosphere. One of the ways that you can try to detect life is to detect, to detect gases that are emitted by life. There are certain gases, such as methane, that we wouldn't consider to be present. We wouldn't consider them to be possibly present in the Martian atmosphere in large quantities because they would break down. Methane is one of those gases, and methane is produced by life forms as well as other processes that don't involve life. But methane is produced in the breakdown of food. I won't go into more detail, but it's produced by all kinds of creatures, including bacteria. And this methane in the Martian atmosphere we know is cyclical. It varies over the course of the seasons. Mars has seasons just like Earth. This could be the result of microorganisms underneath the surface of Mars. We know, can be quite sure, that's what I mean by know, we're very sure that there's no life on the surface of Mars. We very likely would have found it by now, but we've only really been able to explore the first maybe inch or so of the surface of Mars because we don't have technology on Mars which can dig, let's say, 1 meter or 2 meters under the surface. But we hope to be able to do that in the future, and it's possible there's bacteria down there. I should say that there's other ways to produce methane, so this isn't necessarily evidence for life, but it's just a tantalizing clue that there could be. I should also say that Curiosity has detected radiation levels on Mars which are too dangerous for humans. Even though Mars is farther from the sun than is Earth, because there's no atmosphere, there's basically no atmosphere from the perspective of, let's say, a human, then therefore that means that a far larger amount of the radiation can penetrate the atmosphere. I talked about what Earth's atmosphere does for us. It provides us with pressure we need to live. It provides us with oxygen. Those two things we know. Something that the latter one especially people know. Something that a lot of people don't know is that Earth's atmosphere is opaque to the most dangerous kinds of radiation. I mentioned this in the video, I always forget which video is which, I think the video on Earth and the Moon. Earth's atmosphere has a very large opacity when it comes to most forms of radiation, particularly gamma rays and X-rays, and then somewhat when it comes to UV radiation. By opacity, what I mean is the atmosphere is opaque. It doesn't allow the radiation to go through. It blocks the radiation. And that's very important because UV radiation is quite dangerous, and a lot of it is blocked, although not all of it, obviously. Since you know when you go out in the summer, you get sunburned if you don't put on sunscreen, or you could. That's due to UV radiation. But X-rays and gamma rays are really dangerous. They're far more dangerous than UV radiation, and just having sunscreen wouldn't do you much good. That's why when you go to the dentist and you get X-rayed, or when you get X-rayed somewhere else, a doctor's office or whatnot, you will get a lead suit. That's to protect parts of your body from X-rays, which are actually quite dangerous. On Mars, since there's not much of an atmosphere, this radiation really passes through, and therefore, if humans are to go to Mars, they're going to need some kind of protection. All right, I belabored the point just a little bit. Before we go on, I just want to mention in this lecture in particular, I have a lot of links. Feel free to follow the links here. I cite my sources here, so you can read as much as you like if you follow these links. This is a really nice video that I want to have you watch on the Curiosity rover and a little bit about Opportunity and Spirit as well. It's really well done. I would like you to pause now and watch this video by Kobe Boykins, who is a NASA engineer. And he talks about his passion, which is Mars rovers. Please watch this video that I posted to Blackboard, and when you're done, come back to this same point in this lecture video. Let's talk about some of the findings a bit further, and also let's look at some photos. This is a picture of Gale Crater. I unfortunately don't have the source, but I believe it's Curiosity that took this photo. But in any case, it depicts wind erosion on Mars. These rocks have been exposed to the surface. I'm sorry, I'm not highlighting this properly. Have been exposed to the surface for only about 80 million years. Geologists evidently can determine this by looking at rocks. I'm not a geologist, and this is not a course in geology, but nonetheless, geologists study rocks, and they can determine that these rocks have been exposed for about 80 million years, which is evidence of liquid water. Once again, more evidence of liquid water. This is a really excellent video on some of the Mars findings from NASA. Once again, I'd like you to pause this video and pause the video you're watching now and watch this one, Sample Analysis at Mars. Let's now talk about whether we can send people to Mars. I mentioned a couple times in this video that there are some differences between Mars and Earth and some similarities. One of the similarities between Earth and Mars is that Mars has a day which is nearly the same length. This is really excellent since we humans have a natural rhythm. We need to sleep about 7 or 8 hours a day. Not all of us do, but our rhythms are affected by light. There are actually some people on Earth who live in very northern and very southern regions where for at least part of the year it's light outside all the time and dark outside all the time. But this is pretty rare. The vast majority of humans live in places where there's a normal 24-hour cycle of light and day. I'm harping on this point, but anyway, let's put that aside. That's one similarity. Let's talk about some of the differences and some of the challenges in just getting people to Mars. First of all, sending people to Mars is much harder than sending people to the moon because the moon is much closer. It's a little bit hard to visualize how much closer, but one thing you can do is just divide the distance to Mars by the distance to the moon, and what you get is a number equal to about 1,300. Let's try to think about this in local terms. Let's say that you were to walk to your favorite supermarket or deli or pizza place, which is a mile away. That's not a particularly long walk. Let's say it's half a mile there and half a mile back, so it's a mile in total, for the sake of argument. What would be the corresponding distance that you'd have to walk if you were going 1,300 times as far? Well, 1,300 divided by 2 is 650. So you'd have to walk 650 miles and then 650 miles back. That would be how much farther Mars is from Earth than is the moon. That's the equivalent. Obviously, it's far easier to walk a mile than 1,300 miles. I don't have to convince you of that. And this enormous distance actually gives rise to a couple of very difficult problems to overcome. One is that zero gravity is very harmful to the human body. We know from sending people to the International Space Station, which orbits Earth, that the human body degrades in zero gravity very quickly. Muscles, tendons, ligaments, and bones degrade if they're not subjected to forces. And basically all the forces that your body is subjected to 24 hours a day come from gravity. Astronauts in space will exercise for hours every day. And even so, they still suffer from bone loss and muscle loss, etc. In fact, they lose about 1% of bone density per month. We have good data on this because we've been sending people to space for quite some time. This may not sound like a lot, but elderly people lose about 1 to 1.5% of bone density per year. So we're talking about young, healthy people who are losing bone density at a rate about 10 times greater than that of elderly people. Weightlessness might also be able to cause other problems such as vision problems and kidney stones. Another problem is, before I go on, so this evidence here comes from sending people to the International Space Station. I always forget the record for the most time that someone has spent continuously in space. I think it's about 10 months, 9 or 10 months. Every time I look up the record, I find that I've forgotten it, but I think it's about 8 or 9 or 10 months. And unfortunately, if we send people to Mars, we're going to have them in zero gravity for around twice this long. It takes about 6 to 8 months to get to Mars. You'll be in zero gravity during that time if you're going to Mars. Once you get to Mars, you're not in zero gravity, but remember, gravity is only 38% that of Earth, so you're still in reduced gravity. And then it takes 6 to 8 months to get back. Extreme isolation is also quite harmful. I just mentioned that astronauts will have to be waiting in space for 6 to 8 months before they even get to Mars. And this might produce psychological problems. We're not going to be able to send people in a craft the size of a city. You're not going to have football fields and pools and whatnot. These people are going to be in very cramped quarters. Space contains very dangerous radiation and tiny pieces of rock. These tiny pieces of rock, called meteoroids, can travel at tremendous speeds. It can actually damage or even destroy craft. I just want to make an observation here, which is that if you send someone to the moon, the danger from radiation is not as great as if you go outside of the Earth-Moon system and you go out into the solar system. And the reason is that in the Earth-Moon system, you're protected by the Earth's magnetic field. That's one reason. You're also protected somewhat by Earth's gravity, which will soak up quite a bit of the rocks and whatnot. Earth's magnetic field protects us from radiation that has a charge. For example, little protons that are traveling at tremendous speeds, we call these cosmic rays, will get captured by Earth's magnetic field. And therefore, if you're within the magnetic field, even if you're out of off Earth's surface going to the moon, you're still protected to a good degree. Once you go out very far away from Earth toward Mars, you're now completely unprotected. I do want to mention one thing regarding radiation. You can find interviews of astronauts who have been on the International Space Station, who will say that they experienced brilliant flashes of light every once in a while. They will just be in the International Space Station with their eyes closed or eyes open or what have you, and then they'll suddenly see a brilliant flash of light. And we believe this actually comes from these cosmic rays, which are traveling at tremendous speeds, slamming into some part of the astronaut's eyes or brains or whatnot, and then causing these brilliant flashes of light. When a cosmic ray hits an object, whether it be a human or the atmosphere or whatever, it will produce this shower of particles, this energy, and this can induce dangerous biological effects. I just want to point this out. And this problem will become more acute if we send people to Mars. Let's talk about the distance from Earth to Mars and try to draw it to scale. This is very difficult to do, but I've attempted to depict the distance from Earth to Mars to scale here. This is the distance from the Earth to the Moon. It's this distance here in the horizontal direction, not in the vertical direction. It's very hard to depict this because it's very tiny, but it's probably just a couple of pixels here. The distance from Earth to Mars would cover the entire slide. So maybe this is not the best visualization, but the idea is that the distance from Earth to Mars is about 1,300 times the distance from the Earth to the Moon. There are current missions that are on their way to Mars. One is Mars 2020. I'm going to talk about this in a different video. So this is it for my discussion of Mars and the current and past missions of Mars. Please make sure to watch the videos that I referenced in this lecture. They're really important. I think you'll enjoy all of them. In particular, a couple of them I think are some of the best videos that we have in this class. So anyway, thank you for watching this video, and I will talk to you in another one.